Minutes to get that nonsense to boot. I will begin with a word of prayer. So, Heavenly Father, we thank you for this day. I thank you for these students for the weekend, and just pray you be with us today, Lord. Help us to glorify you what we do, Lord. In your name I pray. Amen. Do you guys have any questions about the homework in particular? Well, I'll ask again tomorrow. How about that? So, let's talk about the integral test. So, suppose f of x has graph that looks something like this. All right, so what could you, if the graph looked something like that, what would, let's characterize this. In other words, f of x is continuous, non-negative, and decreasing on 1 to infinity, right? So continuous, you know what that means, right? Non-negative means, what's that mean? That means f of x greater than or equal to 0. What's decreasing mean? How would you define decreasing? It means that a and b in 1 to infinity with a less than b implies that f of a is what? Yeah, greater than or equal to f of b. Although technically, since that allows equality for all a and b like that, I probably should throw in another condition, which is the limit as x goes to infinity of f of x equal to what? What would we like? 0, I think, yeah? Now, so this thing I wrote in blue, it's not how you guys think. How do you guys think about decreasing? What if we taught you in Calculus 1? How do you check decreasing for a function, function of continuous variable? Slope is what? Slope is negative, right? So we tend to take this and trade it for df dx less than 0 for x in 1 to infinity, right? So pragmatically speaking, for a given function, that's often the right way to check that thing's decreasing, all right? Okay, so given all these terms and conditions, what does this have to do with series, right? Well, the thing it has to do with series is very much related to the conversation we had previous in the course about left and right endpoint rules, right? Like if you consider an equal to f of n in this context, right? Then let's see here. The sum n equals 1 to infinity of a sub n is equal to what? That's equal to a1 plus a2 plus a3 plus dot 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 dot, right? So what's the first point on my graph as I've drawn it here? That point is 1, comma what? F of 1, yeah? Because I'm looking at the graph y equals f of x here, okay? And then, so A1 is what? That corresponds to the area. And This can't happen, can it? Look at that. Is that allowed? Decreasing, right? So my graph isn't quite right. What's it have to look like more? Like that, right? Decreasing. So with that in mind, notice that we could draw A1 like this, right? See that? The area of this rectangle is A1, isn't it? Yep. Yes. Because the connection between the series and the function is connected at 1. But you could write we could make a corresponding picture at 0. I'm going to do it at 1. But I hear you. So next up here, if I go over to 2, right, the area of this rectangle would be A2, right? And what's the height? A2 here, f of 2 equals to A2 is the height of that second box, right? And you keep going, right? Right, like over here, that'd be A3. This would be A4, right? So what does this show us? I think it's intuitively clear that the integral from 1 to infinity of f of x dx, right, which would be the area what? If you'll allow, I really don't want to do it, but you guys, please look at me look. So it's the area that's like here, right? That would be the area under the curve, right? How is that related to the series? A1 plus A2 plus A3 plus ... They should be equal. See, I think it's clear that this is less than, that's greater than or equal to what? Not the series, but what? Where does it start? Two, right? Because this is kind of an oddball, isn't it, in this picture? But what if instead of kind of looking at the right endpoint rule relative to this 1, 2, 3, 4, 5 set of points, what if we looked at the left endpoint rule? What would that show us? If you'll allow me to clutter my picture a bit, you could take this A1 and flip it over, right? And you'd have like this, height A1, height A2, right? Height A3. And if you look at under the red stair step, right? You can see that that's going to be above the improper integral from 1 to infinity, right? So I think it's intuitively clear in this situation, supposing, of course, that the series converges for the sake of discussion, I think you should be able to see that this is less than or equal to what? The series itself, right? So that's by the red picture. This is by the blue picture. If you'd like, I can draw them separately. Yeah. Because if you look at it, this first box isn't under the black curve, right? Just 2, 3, 4, 5, and so forth. So the area under the... Fine, let me draw a summary picture, since people are not entirely with me here. So here's the honest to goodness this, all right? So this, of course, would be the integral from 1 to infinity of f of x dx if it exists, right? And the blue picture I was trying to draw is that, oops. So this is A2, A3, A4, A5, so A2 plus A3 plus A4 plus dot 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 is less than or equal to. That is less than or equal to I think this marker's dead. I mean, actually, this estimate I'm suggesting, it makes sense whether or not the improper integral converges or diverges. I mean, we could just as well compare like a limiting definite integral that's used to calculate the improper integral, and we'd have the same estimate. What I'm trying to say is it's reasonable to suppose that if the improper integral diverges, then the series what? I say if the improper integral diverges, then the series diverges. Does that make sense why that would be true? Because the improper integral is less than the series, right? And you can, I mean, you could replace infinity with going out to a certain point, right? To give a careful proof, but this is the theorem. Given f of x as described over there, okay, we find two things. One, well, actually three things. If the integral from 1 to infinity of f of x dx diverges, then the series n equals 1 to infinity of a sub n diverges. And this is, of course, for what? For a sub n equal to f of n, all right? So I'm sticking with the notation I've laid out so far today. Point 2, if the integral from 1 to infinity of f of x dx converges, then the series sum n equals 1 to infinity of a sub n converges. Moreover, what can we say? What if instead of going to, so think about everything we've done so far, right? What if instead of going all the way to infinity with our picture, suppose we stop the picture at something else, like, you guys pick a letter for a positive, like let's say I need some letter. G? Okay. So suppose we stop it at G. I'm going to make it a big G. There we go. And so, I mean, that's a natural number, okay? So in other words, we're going, so there's some kind of break in the graph, right? And eventually we go out here to big G. So what would that tell us? That would tell us the sum n equals 2 to what? G? Careful. G minus 1 of a sub n is less than or equal to the integral from 1 to g of f of x dx is less than or equal to the sum n equals 1 to g itself of a sub n. Because that's where the left one goes to. Oh, wait a minute. Oh, you're right. It would be G. Yeah, I got it backwards, don't I? Thank you. That one should be G because it goes to G. It's the red one, right? That's based on the G minus 1. Fair enough. You got me. Thank you. Much appreciated. So that actually gives us a specific estimate, right? What's that tell us? Yep.
Question about the theorem. Why is it the sum is n equals to 1, a sub n converges?
What do you mean?
Part 2. Why does it converge? Because isn't that greater than?
Well, if the, let's see here, how to say this. If the area under the black curve is finite, right? Then the sum n equals 2 to infinity clearly is less than that, right? So if I just add a 1 to that, that gives me the whole series. So if something converges and then I add one term to it, it's still convergent. So you're right, it's not a direct comparison, there's like an extra logical step there. And that same logical step is what's involved with me writing the following. So we look at the gth partial sum minus what? On the left, we have SG minus what? Minus A1, right? So SG minus A1 is less than or equal to the integral from 1 to G of f of x dx, which is less than or equal to what? The G minus 1th partial sum. Oh, excuse me. How could I get all right, fine. Anyway, I'm getting too far into the weeds here today on this. Well, I'm just going to kind of stick a thumbtack in this for later. When we need to come back and discuss about, how close a given series is to what it converges to, this is useful. It gives us a precise estimate between the G minus 1th and the G partial sum and this particular integral. Let me see if I can be more precise here. Let me give a specific example to try to explain what I'm talking about here. We have calculated before the integral from 1 to infinity of dx over x squared is what? This was the p equals 2 integral, remember? What did it work out to? Was it 1 over p minus 1, or? I'm trying to remember. Do you want me to put a 4 here to make it more interesting? I mean, I'll keep it like, I think it's 1, right? It's 1. Because it's 1 over p minus 1, which is 1 over 2 minus 1, which is equal to 1. So here, p is equal to 2. Right? So running through this thought process here, this is, by the way, this is the so-called integral test. All right. The thing I'm quibbling over is not the integral test, it's the integral test estimation theorem, which is kind of an add-on, all right? Which if I had more common sense, I'd wait till later when you guys are not overwhelmed by what I'm doing at the moment. All right, so my question is, how does this compare to, so let's consider the series, sum n equals 1 to infinity of 1 over n squared, right? This is 1 plus a 4th plus a 9th plus dot, 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 dot. This is the so-called p equals 2 series, all right? So my question is, you know, if I call this, what's the error in, say, the difference between the full p equals 2 series and let's just keep, oh, I don't know, the first 3 terms. So this would be the error in the third partial in S3 here, I think, yeah? We can use this S sub g estimate to pin it down, right? But rather than do that, I'm going to go back to my picture and go, okay, so, well, actually, maybe not be an idiot. Ah, hey, I got my shirt. Aha. It was here all along. Let's see here. So what's this say? This says, let me just do it. It says S3, right? What's A1 in this example? 1, right? Is, curses, that's not what I want. I mean, this is true, but it's useless to us. Don't erase this from your notes. It's not wrong, okay? Leave it there. But I'm interested in what this said. This said that the series, starting at 2, which we could rewrite as n equals 1 to infinity of a sub n, you know, minus a1 plus that is less than or equal to the integral from 1 to infinity of f of x dx, right? Is less than or equal to what? The series, the full series. So what's that say? Oh, ay, guys. Curses. I don't even know what I've done. I mean, it's not wrong, it's just not right. Again, that is true, but how does it help me bound the error in the third partial sum of the p equals 2 series? Well, I'm sorry, folks. We'll have to come back to this. Because I'm missing some critical building block here at the moment. Sorry about that. So let's go on. The theorem, which is known as P-series, is as follows. The sum n equals 1 to infinity of 1 over n to the p is as follows. It diverges for p greater than or equal to 1, and it converges for p. Oh, I got it backwards. That's supposed to be p less than or equal to 1, right? For p greater than 1. So let me, before I talk about the proof of this theorem, let me just some, particular cases. The p equals 2 series, right? N equals 1 to infinity of 1 over n squared converges. Whereas the sum n equals 1 to infinity of 1 over the square root of n, aka the p equals 1/2 series, which of course is less than 1, diverges. So this is the so-called p series, all right? This is a benchmark series that we're going to use much in the same way you've been using perhaps the 1 over, the p integral as a used for comparison purposes in your homework maybe, right? So how do we prove this theorem about p series? How about this? If p is less than or equal to 0, then 1 over n to the p is equal to n to the minus p, where minus p is greater than or equal to 0. Thus, 1 over n to the p does not go to 0 as n goes to infinity, right? If we have n to a positive, or if the exponent's 0, it's just the constant function 1, which does not limit to 0, right? If, on the other hand, minus p is a positive thing, right, then that would mean what? If p is equal to minus 1, for example, right, then 1 over n to the p is actually just n. And what's the limit as n goes to infinity? Well, it's just infinity, right? I mean, so this is, again, the case, and so therefore what? In this case, diverges by what? What's my logic here? Why do I know it diverges? In this particular case, if p is less than or equal to 0. That is true, but I'm trying to prove why that's true. I can't use that. What's my logic? I mean, so to draw the cases, if this number line's p, I'm making an argument for p less than or equal to 0. Like over here, this is my case 1. What am I using? Why do I know that this diverges? I've argued that 1 over n to the p does not go to 0. Therefore, this series diverges by the what? Nth term test, right? Let's look at case 2. P would be what? What's the other possibility? P is not less than or equal to 0, but p is greater than 0. Then f of x equals 1 over x to the p, right, is what? Is continuous on 1 to infinity. And you guys like this. What's df dx equal to? df dx is minus p over x to the p plus 1, right? Differentiate the minus p power, we get minus p minus 1, otherwise known as 1 over x to the p plus 1. So that's just the power rule for derivatives, right? And, well, That's less than 0 for x greater than or equal to 1, right? Thus, f of x equals 1 over x to the p is decreasing. And what else do we know? It's decreasing. What else? I mean, I'm supposed to check it's continuous, non-negative, decreasing, limit 0. So is it, I said it's continuous. Moreover, f of x equal 1 over x to the p is certainly greater than it's certainly greater than 0, right? For x greater than or equal to 1, and the limit as x goes to infinity of 1 over x to the p equals to what? Is 0, right? How do I know that? Because p is positive, right? If p were negative, I couldn't say that the limit as x goes to infinity of 1 over x to the p was 0, right? If p equals minus 1, this limit is not 0, right? Do you guys know what I'm saying? If p was minus 1, this wouldn't be true, right? But we're assuming we're in case 2 where p is positive, right? Ow. So I have done what? I have certified, we have satisfied the terms and conditions of the integral test, right? Therefore, the convergence or divergence of the p-series, in this case 2, is inextricably tied to the convergence or divergence of the corresponding improper integral from 1 to infinity, which we've already discussed, right? The integral from 1 to infinity of dx over x to the p is what? It converges for p what? Greater than 1, and it diverges for p, less than or equal to 1. We conclude the theorem is true by the integral test. I don't even, to be clear, I'm not even using the full, I'm only comparing the improper integral to the series in what case? In the case 2, right, when p is positive. So I'm not even really using the full test we found for the integral, because when p is less than or equal to 0, I actually use the nth term test instead to prove divergence in that case, okay? So I'm sorry I have muddled the estimation today. I'll work on that tomorrow. I'm sorry, guys. So look at some examples. So if we look at 1 plus 1/2 plus 1/3 plus 1/4 plus ... That's what? That's the sum. N equals 1 to infinity of 1 over n, right? So what's the deal with this one? Converge or diverge? Yeah, this is the p equals 1 series, which diverges by the p series result. this theorem is the P-series result, okay? It suffices going forward for you to tell me this diverges because it's a P equals 1 series, right? And to be, I mean, just to be clear, P is what? P is greater than or equal to 1, right? I keep messing it up. Less than or equal to 1. In contrast, 1 plus a fourth plus a ninth plus a 16th, this would be the sum n equals 1 to infinity of 1 over n squared, right? This is the what? P equals to 2, which of course is greater than 1 series converges. Let's see here. Oh, let me just stop writing. Are there any questions about this? Yeah.
Can you use the P-series test, or like can you use the P-series like concept and the direct comparison test at the same time?
Is there? So your question is, is there a comparison theorem for series? Because I've told you guys about the comparison theorem for improper integrals, but we haven't. But you're right. There is in fact a comparison test for series. That's true. I'll state that in just a second here. Before I do that, though, just a little bit more language. So example 1, this P equals 1 series is so important. It's such a crucial example. It has another name. This is also known as the harmonic series. And I will admit, why is it called the harmonic series here? I don't know if I don't think I actually know the reason for that, honestly. Yeah, you know? Because it like blows up because it's like that divergence or
Well, in a way, like your fundamental frequency is like at 1, and then if you cut that in half, you have, like, of course, an octave higher, and then if you cut that a third, you have the fifth pitch, a perfect fifth pitch above that, which is an octave and a fifth above.
so all of the divergent. You're thinking of all the different divergent cases as various, but the harmonics.
The harmonics work in the violin, and the way that pitch.
Huh. I don't know. I mean, that's an interesting thought. I guess in your thinking, all of the divergent cases are different sort of harmonics of the basic harmonic.
There's an infinite amount of harmonics which are sounding above and below from the instrument, which, depending on what harmonics are like most prevalent, creates the timbre of the instrument.
Right. Huh. I really don't know. But P equals 2, as far as I know, doesn't have a name. I mean, well, you could relate it to the Riemann zeta function. But it turns out that this actually converges, and this is not obvious, to pi squared over 6. This has been known since the 18th century. Euler derived it 1730s or something. But why is that true? Well, I only will give you an answer to that at the end of the course. We need something called Fourier series to derive this, actually. So anyway, deciding the convergence or divergence of the series is relatively simple. The question is it something that's not going to 0 as fast as, if it's going to 0 as slow as or more slowly than 1 over n, all right, that's not going to 0 fast enough to make the series converge. If on the other hand, if the series has terms in it which are like going to 0 in a way which is similar to something like 1 over n squared, or even 1 over, just to be clear, guys, if I have the sum n equals 1 to infinity of 1 over n to the 1.00000000000, take the rest of your natural life writing 0, and then put a 1, all right? That converges. So this harmonic series is like right on the bubble of divergence, all right? Anything even going to 0, it's slightly a little bit faster in this sense, will converge, all right? But a caution, right? 1 over n goes to 0 as n goes to infinity, but the sum, n equals 1 to infinity of 1 over n, diverges. This is, we cannot just reverse the logic of the nth term test, right? If the term in the series does not go to 0, that implies that the given series diverges by the nth term test. On the other hand, if a sub n goes to 0, that doesn't really tell us anything. If a sub n goes to 0, it might be convergent, right? Like example 2 or example 3, but it might not, like example 1. Comparison test. So there is a comparison test. So the first comparison test, so-called direct comparison test, which I will abbreviate sometimes as DCT, says if 0 is less than or equal to a sub n is less than or equal to b sub n, then numero uno, if the sum over b sub n converges, then the sum over a sub n converges. In number 2, if the sum over a sub n diverges, then the sum of the larger series b sub n diverges. Of course, there's also an estimate that comes in the first case, right? Like the sum of the series for a sub n is going to be less than the sum of the series for b sub n in the case that it converges. Like there's also that aspect to the direct comparison test. So let's see here if we could think of something. A silly example, something like, I don't know, sum n equals 1 to infinity of 1 over n squared plus e to the n, maybe. Is that going to be something I can, right? I can think of that as being my b sub n, right? And that's less than or equal to what? 1 over n squared. Why does that matter? And I start to give these things a name. I'm going to call the original series S. Thus, S converges by direct comparison test with p equals to 2 series. It's clear that we're looking at a series with positive terms, right? E to the n is positive, n squared is positive. Now, direct comparison test is you know, it's a nice tool, but next time we'll talk about the limit comparison test, which is an even more sort of greedy tool. Finally, gentleman in the back, you started asking me about a homework question at the end of last class, and I had a hint for you guys on that I wanted to share with you today. What was it? 1 over x to the 5th minus 1, was it? 1 plus x to the what? To the 5th?
It was x to the 5th inside the parentheses, and then on the outside of the parentheses, it was 1/6.
1 to infinity? So, you found something to compare to for that one, right?
Yes, but then I didn't think it was correct.
Oh, you didn't think it was correct? All right, all right. Let's see here. So the intuition is what? 1 over 1 plus x to the 5th to the 1/6 power is sort of asymptotically going 1 over x to the 5 over 6 for x much greater than 1, right? For x much greater than 1, that 1 is essentially irrelevant. We're just left with 1 over x to the 5/6 power, right? So as just an intuitive calculation, we're going to say that this, what's our intuition? Does this converge or diverge, this integral? Right, so we expect this, we expect. But, to be careful Calculus 2 students, we should actually come up with an estimate, right? So I don't know. So the trouble is, of course, as much as we'd love, I mean, wouldn't it be great if that was greater than or equal to 1 over x to the 5/6? But that's not true, is it? Because what did we do going from one side to the other? The denominator in the right-hand side is larger, which makes the fraction smaller. So that inequality is just false, right? It's false. So how can I manipulate x to the 5th plus 1 to make it something more like, I want x to the 5th plus 1 to change into something that's more like stuff to the 5th minus positive stuff. If that makes sense. If I could do something, if I could make some kind of substitution where that happened, that would probably do it for me, right? Sometimes you can make a change of integration variable to make that happen. Something like maybe u equals to, I don't know. Let's see what happens if we let u equals to x minus 2. What does that do? Maybe x plus 2. If we did u equals x plus 2, then x is equal to u minus 2, right? So then x to the 5th is what? Well, anyway, there's no hope of me finishing this at the moment. I'm sorry, I'm over time, but this is an idea that might help with that. I think that's a hard problem.